I'm Andrew Butler. I work under the Code A team and primarily have worked on projects like Trusted AI and different components of the Kubeflow project, including KFB Tekton, KF serving, a little bit of Kubeflow pipelines as well. This particular session will be on distributed training and hyperparameter optimization. I'll give you a bit on distributed training. Kevin will give you some information about the hyperparameter optimization, and then Kevin and Tommy, I believe, have a demo to show at the end as well. So specifically what we're looking at is training operators, and inside of those we're looking at the Tensorflow operator, the Pytorch operator, and the Mpi operator. And then we'll also be looking at the Kubeflow tools for hyperparameter tuning, and that'll be catted. And so we're going to talk a little bit again about distributed model training operators. And so that will get into Uber's Horvath backend a little bit as one of the Mpi operators that's very helpful in distributed training. And also for hyperparameter optimization, we'll talk about how catted can be a successful tool that you can use to avoid some of the common problems in hyperparameter optimization. So just going over it one more time, we're going to talk about the TF operator, which is using the TensorFlow distributed backend, the Pytorch operator, which is the Torch distributed backend, and then Uber's Horvath's Mpi operator, which will use the Horvath distributed optimizer backend. And so in traditional model training, in the way past, we could have an entire data set, let's say MNIST, the entire model, everything that we would need in one machine, and there would be no real issues with that. But nowadays, as things get larger and larger, the data sets, each image is now, it's no longer a 28 by 28 image, it's now could be, hundreds of thousands of pixels, and the models could be billions of parameters. It's not necessarily so clear how we can house it on one machine, and obviously we can't just make the one machine as large as possible. So it's not always going to fit the entire model inside of it or the entire data set. So while this has worked in the past, we may need to change it up in the future. And so that's the need for distributed training, is that models are too large for a single device. For example, AlexNet, which is the picture to the left, has some 60 million parameters. And the way that they were able to house it, I believe AlexNet was from 2012, they used 2 GPUs instead of a single GPU for training. And that both greatly sped it up, but also made this experiment possible because the GPUs they had at the time were much smaller than what we have access to today. But also there's another need for distributed training, and that's improved parallelization. With the use of multiple machines for model instance, we're actually able to see a very large training speed up. And that this gets better and better as the models get larger and larger and have more and more parameters. So you can see that for something as large as 2 billion parameters, if we use 64 machines per model instance instead of 1, we see a training speed up of about 10 times, which, especially in today's climate where we need to iterate quickly on artificial intelligence and machine learning systems, if it's medical imaging, whatever it might be, these speed ups can help greatly. And so distributed training can be used to great effect. So what does that actually look like? Here's an example of distributed model training. This is specifically as a parameter server. And just to give you a little bit of an insight onto, if you're familiar with the ML flow generally, here we have each worker. Should be a set of M workers that'll be predefined, and then there will be also a set of servers. But in this example, we're looking at one server and their model or their worker pairings. And so first, each worker will take a piece of training data. It will compute the gradients based on forward propagation and then back propagation. And then it will push these gradients to the server, where the server will then combine the gradients. This could be done as simply as through summation or more complex forms. And then we will update the weights and send the weights back to the workers, where they will rinse and repeat the process over and over. And so this allows us to, essentially get a larger and larger batch size if we have multiple workers, because we can have them going in parallel at the same time. And so, like I said, this is actually an example of parameter server that we saw in the past. And this is the most simple form of distributed training and often the most common because it is very simple to implement and does not take a lot. But again, it's just one centralized parameter server, and it collects everything that the worker nodes does and combines it and then sends it back to the worker nodes for them to do more work as is needed and repeating the process. And so to look more in depth about what that actually looks like, we're gonna look at it step by step. So this is just an example where the parameter server is also a worker. This is an easy enough change to make and doesn't really change the process too much. But in step one, we have each machine, it takes the parameters and it does whatever updates it needs on those parameters. And then in step two, all the parameters from each of the other machines are aggregated on machine A. And then this gives us the step three where machine A actually combines each of the parameters. So each A1, B1, C1, D1 are an updated parameter, or is a gradient for parameter one. And so by combining these, again, we can create the new weight that we would like to pass back to all the machines, which is what we do in step four. We pass all the parameters back so that we end up on the same page for each machine. And so this is great, but as you can see in step three, we kind of lose a little bit of work. So in machine A, because it has all of the parameters, it is doing all of the work while machine B, machine C, and machine D are idle. This is obviously isn't optimal, and so the idea is what can we do to help make the workloads spread out across more machines and distribute this a little bit better. So that's where AllReduce comes in. AllReduce is a more parallelized form of distributed training. And there's a bunch of different types and styles of AllReduce, and each of them have their different benefits and costs. We're just going to talk about the more basic one, but there's also tree AllReduce and ring AllReduce and a few others if you're interested in looking that up. And so what this looks like is same thing in step one. All the gradients are computed for each individual machine. And then in step two, this is where it gets a little bit different. A machine A takes all of a certain type of parameter and machine B takes all of a certain type of parameter. So you can see that machine A has collected parameter one from machine A, parameter B, or parameter one from machine B, parameter one from machine C. And it's what we're going to do with that is actually, this allows us to, in step three, parallelize the computations a little bit, where machine A is able to compute parameter one completely, and then machine B computes parameter two completely. And then this allows us to get all the machines working and having workloads. None of them are idle. Well, there might be a little bit of idleness based on how fast each machine is, but it's much less than what we had in previous sections where the entire workload was on machine A. And then step four is the same, where we distribute all the parameters back out to each of the machines. And so some of the advantages of AllReduce style training, besides what we've already talked about, which is parallelizing the workflow or the workloads a little bit and not having idle resources, it's also useful because each worker stores a complete set of model parameters. So if there's various reasons why we would want to add more workers, and we'll talk about that in the advantages as well, but adding workers is easier because it can just go to any other worker and ask for the full of it. And so, for example, if a worker does fail, it is easy to recover it because restarting that failed worker and loading the model only needs to be done from any of the other existing workers. And so we just choose the worker with the smallest current workload, and we can repurpose it from there. And again, models can be updated more efficiently by leveraging network structure because, again, we've parallelized it a little bit. Any model can go to the model with the least amount of workload to pull the new updated parameters, and that'll be helpful. And then also scaling up and down workers only requires reconstructing the underlying AllReduce communicator and reassigning the ranks among workers. So if there's one underlying controller on the entire thing, we just have to go and talk to that controller and decide where the new parameters distribution should be. If it's a model parallelized. And if it's data parallelized, we just figure out where data needs to be passed. And so now we'll talk more specifically about distributed training in the Kubeflow environment. And so the three main ones, there's a few more, but the three main ones are TF Operator, like we talked about, Pytorch Operator, and Mpi Operator. There's a few other ones, but these are the largest, and I believe a couple of the other ones have been discontinued slightly. So the first one, Mpi Operator, it's the all reduced style distributed training on Kubernetes. So this is very useful. All of the other ones are using the parameter server training. So this gets you a lot of the performance benefits that you might not get in the other ones. And this is especially helpful because the Mpi operator is actually decoupled from one machine learning framework. So you can use many different machine learning frameworks as you see fit. And it's all under one custom resource definition. And so we're just going to quickly go over the design of how this works. So when a new MPI job is created, there's a certain set of steps that are done by the MPI job controller to launch the job. The first is to create a config map, and then we create the RBAC resources to allow remote execution. We create the worker stateful sets. And then once that happens, we have to wait for the worker pods to be ready because there's many things associated with that will take time. And then we'll create the job, which is run under the service account. And so that's the basic design flow for this. You can see the diagram on the right. And so what exactly does this look like? So what we end up with is an example API spec for how to implement this. And so at the top, you see we have MPI job for the custom resource. And we've defined a little bit of metadata. But more importantly, we need to look at the spec and the MPI replica specs. So the MPI uses a launcher format. So we need to define a launcher, and we've decided one replica of that launcher. We can decide what containers, what images we use in the containers. And then as well as in the command section over here, we decide what necessarily we want to use from that image. We can pass certain things that we might need if we want to use the ResNet 101 model, what our batch size would look like. And then similarly in the worker spec, we defined two replicas, and we've given the same container but with slightly different information, and we've set a resource limit of 1 GPU for each worker. And so from your perspective, working on the MPI operator is what's important. So the roadmap of MPI operator changes that needs to happen might interest you, what you might be able to work on in this project. So there's very basic support things like support installation of MPI operator via Helm, support new versions of MPI operator and Kubeflow manifests. But there's also more interesting things like decouple the type dependencies on MPI and support other collective communication frameworks. This might be useful because we have a large breadth of machine learning frameworks that we can use, and why don't we append the ability to use other collective communication frameworks as well. That gives us a bit larger breadth of options to use for this. And there's more things like CI/CD and bug fixes, and we don't need to go over every one. You can find the roadmap on the GitHub and see what might interest you and look at the related issues. So now we have TF operator. So TF jobs are the MPI job equivalent, or the TensorFlow equivalent for TensorFlow jobs on Kubernetes. And so the TF operator is the Kubeflow implementation of TF jobs. And like we talked about, TF jobs typically use parameter servers. So you don't get some of the same benefits that you get from the MPI operator, but they're still useful in their own right. And so TF job is a collection of TF replicas, and each TF replica will correspond to a set of TensorFlow processes performing a role in the job. And this can vary widely. So to look at more what the collection of processes are in a TensorFlow job, the large one is the chief. The chief is the main orchestrator for everything. And sometimes we will assign a worker to also be the chief. Generally, it's worker 0. But this chief does things like checkpointing the model and anything that might need to be done on a complete level. Parameter servers, PS, that's what we talked about. They provide a distributed data store for the model. Workers do all the work. And again, the worker 0 might act as the chief. And then we also have something called an evaluator, which just computes different metrics that you might want to see while the model is being trained, so that you can kind of keep tabs on the model and see if there's anything going wrong with it. Maybe you want to stop it early and iterate something to get better changes, and you don't want to waste that compute space. The evaluator will help you tell if something's going wrong and you need to do that. And so let's take a look at what the difference is between TF job and MPI job in terms of custom resource definitions. You can see, obviously, we need to define that it's a TF job rather than an MPI job, but also in the spec, we need to say it's a TF replica spec as opposed to an MPI replica spec. And then also we'll change the image based on what it is that we actually would like to train. And then based on that, the command associated with that will be obviously different based on the operator, even though that you could use TensorFlow in either a TF job or MPI job format. So the TF operator roadmap is more simple. There's not as much. Because Google runs Kubeflow, they have a very strong handle on the TF operator as well. So Q1 and Q2, better log support, validating webhook, and better Volcano support for Q3 and Q4. Again, this will just be on the GitHub page if you'd like to check it out and see the related issues. And so lastly, we have the Pytorch operator. Again, the identical thing for Pytorch jobs on Kubernetes as TF jobs and MPI jobs were for their respective operators. And there are a number of metrics that can be monitored for in the Pytorch operator using Prometheus Monitoring, and these can help you know, kind of similar to what the evaluator does in TF job, but there's also a few more things that you can get with Prometheus Monitoring, which we'll look at. So first of all, if we look at metrics for each component container, if you need to know the CPU usage, the GPU usage, you know, how much of your thing is working, keep a live check. There's a few more. I think there's roughly 10 in total. And then there's also metrics for reporting Pytorch job information, job creation, how many successful completions, failed jobs, and anything of that sort. So that is it for this. Let me get I'm going to show you quickly what they look like again. So for TF jobs, we have, again, kind TF job, some metadata that might interest us. We've defined a worker. In this case, we only have one replica, but that should work fine for us. And then we've listed our container, our image, and then a few things to give us some specifications based on each individual image, where the logs will be, the learning rate, batch size, volume mounts, and we don't really need to look at that too much. I've already ran these because they take a while to get going and spun up, so we'll just take a look at what we can see after the fact. Okay, so here's the one that we have already ran. And let's take a look at what it looks like. So here we have the TF jobs, what we've defined previously. Everything here is more collected. And then what's important for us is the status, and gives us basically where we're at in this TF job. So you can see we've created the TF job previously. I think I did this about a month ago. Yeah, about a month ago. So we've created the TF job, then we've ran the TF job, and then the TF job succeeded. So that's a little bit of the status. And these are pretty common, again, across different operators. They look very similar, if not identical. So yeah, here you go, replica status as well. We had one worker on this as well. And then we can look at Pytorch jobs as well, which we also, I had done this one previously, so we can just take a look at the statuses.
How many workers are actually used here? All I see is just one worker, or I was hoping
Yeah, it's just one worker in the example, but you could scale up pretty simply. This is just the basic one that they use to show you that it's actually working on your cluster.
Okay.
Yeah, and so this is the same deal for this Pytorch job. Here we actually defined a master and a worker, and so this will get us one one replica of the master and one replica of the worker for the Pytorch job, and we have similar specifications below. But you can see that in the status that we've had, we have all the basic stuff that we talked about, and then we also have the status for the Pytorch job creation, Pytorch job running, Pytorch job succeeded, and you can see that the replicas, we have one master and one worker like we had specified previously. And these are pretty simple to run once you have them set up. So we can just, just remove it, and then we can apply it again. Actually, let's get the Tensorflow one. And then we can look it up again and see if it has been. So now we see it's running. Oh. And now we can see that there's no longer the succeeded section of the status for the TF job. So now we just see that it's created and then it's running, and it'll continue to run for some 10, I believe, minutes. But that's just to show you how easy it is once you have it set up. And obviously there's a lot of work that goes into filling out the images and working from that end, all the specifications for the model building. But for the training, deploying it, it's fairly simple and can be done fairly quickly. And with that, I think I'll hand it over to Kevin. I believe he's going to run us through CATIB. Kevin, are you there?
Yes, I'm here. Can you hear me?
Yeah, I can hear you.
Oh, okay. Can you see?
Yeah, I can see your screen.
Oh, okay. Hi, everyone. My name is Kevin. I'm working with Andrew and under admission for the Kodai team. I'm the contributor for the KFP Tecton project, also other open source project. So today
Kevin,
I'm
I think
going to...
it's showing us a dual slide thing. It's showing us current slide 24 of 45 and next slide 25 of 45. I assume it's supposed to be reversed for the monitors. Yeah.
Oh, okay. Right now it looks better.
Yeah, I can see. I just see the CATIB intro.
Okay, thanks. So today I'm going to introduce you about CATIB, and which is used for the automatic tuning your machine learning models, hyperparameter and neural architecture search. And as you already know, CATIB is part of Kubeflow component. Itself is an open source project. It supports numbers of machine learning framework like Tensorflow, Apache MXNet, Pytorch, XGBoost, and others. So the motivation for the Kubeflow CATIB project is to automatic tuning machine learning models, hyperparameter, and the neural architecture. KDIP is a fully open source Kubernetes native hyperparameter tuning service inspired by Google's Visual. It has extensible algorithm and simple integration with other Kubeflow components. So these are the major components for the KDIP, and they had a database manager. Backend is using MySQL, and has UI and had a if you want to know more information, and here's the link to the GitHub report. So the design principle for the KDIP is from the auto machine learning, which is a powerful mechanism to design and tune models. All the auto machine learning workflow runs in the iterative manner and integrate all models, representation, interpretation function needed by different neural architecture search algorithm into the model manager. And hyperparameter tuning and NAS, neural architecture search, so can be naturally unified in one system. And KDIP is a scalable Kubernetes native auto machine learning platform. So this diagram shows the relationships with the workflow. Here is the system design diagram for the KDIP. This combines the requirements of those auto machine learning workflows and the ideas from the Google's black box optimization tool Visual. Once the user create a study job, CR custom resource, by the way, right now it's called experiment. KDIP controller will create a try controller and a suggestion controller and work together to achieve the hyperparameter tuning for user machine learning models. So here's the instruction to install the KDIP. When you install the Kubeflow, it's a part of the component. You can also install the KDIP individually. So once you install the Kubeflow, and from the Kubeflow's dashboard in the left-hand side, you can click the KDIP and go to the KDIP's dashboard UI. And from the UI, you can try some experimental examples for the hyperparameter tuning. In here, you specify the some metadata, the name and the namespace where you want, the parallel child count, how many you want, child count. It's similar like Andrew just showed in those his operator's YAML file. So once you specify those specifications, then you do the deploy. And from GUI, you can deploy the experiment tool. And you can monitor the experiment from the UI, and you go to the KDIP and click the monitor, and it will show the experimental job there. Then you click for detail, it will see the view the experimental and show the stats. And you can also check the status from the command line. So go to your, later I will show you examples. Use the kubectl experimental with the namespace. And you can check also the detail from the YAML file. Then you will see the specification from the dashboard, which we just show you, and the algorithm and support the KDIP support the random create a couple of other algorithms. And you can also check the child controller. And use the Kubeflow control command to get the status of the child. Also, for the suggestion CR, you can check the status from command line. So here, this is my Kubeflow dashboard. So in the experimental parameters, we can specify the name.
Kevin, I don't think we couldn't see your screen, your
okay.
browser. I mean.
Maybe best to jump to the demo, Tommy. I think we probably can. Okay, so you have that screen. Okay. Okay.
Sorry. Yeah. So this is my Kubeflow dashboard, and you go to Ktip, and in here you can specify the name you want to see and the namespace. And click the deploy, say successfully. And you see the monitor. So I just submitted this one here, build experimental. And if you go to the command line, so you just see the one we currently created.
Kevin, we can't see your terminal.
Oh, sorry. Every time I think need to create a new share. It's different ways. Can you see?
Yeah, that's good. Thank you.
Oh, okay. So I was just go to the command line and show. This is the one we just created. You want to see the detail. So you can see the YAML specification for this one. So after the experimental, it will create also trial. See the here. So in here we had those trial and the source is running, and you can use the same command to get the YAML file. And also another controller category will create is the suggestion. You see there's a suggestion here. So now you see what's happening after you deploy the experimental from the external user perspective. And here is what's happening internally for the category hyperparameter tuning working. After experimental CR creator, category controller will work together with the experimental try suggestion controller to achieve the hyperparameter tuning for user machine learning models. And this diagram shows what the category system will do after you submit your experimental for the hyperparameter tuning. And there is a total 11 steps. And it will be iterated in between those steps until find the best hyperparameter tuning for the models. When it ends, it will record the best set of hyperparameters in the status.current optimal trial field. So now I end my presentation, and my colleague Tommy will show you more complex machine learning examples using the categories.
Right, thanks, Kevin. I think Kevin have shown you like the majority of the demos already. So I will just have back like one of the example we've done on the Kubeflow pipelines. And for these examples, when we actually run it by leveraging the TF job behind the scenes. What Kevin ran before, it was using just a simple container job in Kubernetes. And those configurations you probably could see inside the experiment. So you in a trial template, you should able to tell how do you want to execute each trial, either using a TF job or regular jobs. So for the MX example we executed earlier in the day, we actually used the TF jobs and did like distributed trainings with like one worker node and one master and 3 worker nodes. So we have worker replicas for free, and then master with one master. And let me show you what is actually being ran. So once every run is finished, let me clear it up. Maybe it's better. So after each run is finished, it will just clean up the whole cycles. But I left one of the jobs over here. So for this one, it has like one master we call chef in TF job, and then 3 worker nodes. Each of them are deployed as the stateful set style. And then we also have like a random, we call it a controller to actually inject random parameters in this case, because we're just doing random search. So each trial, we just pick a random set of hyperparameter and search it. And then over time, the trial controller is actually monitoring like the whole overflow. So you should be able to see this value is being collected by each trial CR. And then the selection of the hyperparameter is done by the suggestions. Because it's, so you use, let's say, a group search, then you might just grid over each possible combinations of the hyperparameters. But this case is random, so we just pick a random value between the set of integer we have defined. And you can also use hyperband where you can stop the run in the middle based on its metrics, and then we start another jobs more frequently based on the algorithm you have picked. So that is the end of the Katapp demo. Thank you very much.
Thanks, Andrew, Kevin, and Tommy. We can probably take some questions which are unanswered. I believe probably all are covered for the most part. The last one, Tom is asking, can you specify the distribution strategy when you create your experiment? Tom, can you clarify what you mean by distribution strategy? You're talking more in the context of whether you're running already used algorithm or you're using,
Yeah.
training.
I mean, you are talking about the distributed training that is specified as part of the template. So when you deploy a Katapp job, there's a section you could put either a raw template or a template you uploaded in the database. And inside the template, you could pick like either TF job or other jobs as well. And that TF job will define how you want to do the distributed training, either like one worker node or 3 worker node, or you could also parameterize that worker node based on a hyperparameter you have inputted as well.
And Katapp would respect that, and that's how Katapp would do the hyperparameter optimization.
Right. So you could. So when you define your templates, there's a special syntax you could use to treat those as say variables, and that variables can be injected from the Katapp platform.
Cool. Thank you.
For Cal, I have a question for like, does Katapp work with Cal? So Cal is more focused on the notebook, where Katapp is kind of triggered as a CR. So it's more like Cal is using Katapp, not Katapp using Cal in this case.
And Kale is coming up with, Kale is primarily targeted towards Kubeflow pipeline, right? But Kale is coming up, there is a pending blog, which is going to be published soon, where they have done a lot of optimization to work with hyperparameter optimization and Katapp, right? So that's coming soon. If Josh is still there, right, he can give you more details. But yeah, it's the relationship is, coming from Kale and then leveraging whether Kubeflow pipelines or, hyperparameter optimization in future.
Is it break time now?
Let's look at the Kubeflow